Hi, this presentation will go over the idea of confidence intervals for the mean when we have small samples. So when we have sample size less than 30, we don't use the z distribution, we switch to the t distribution. And here's the formula for that. We have t is equal to our error, x bar minus mu, divided by s, the sample standard deviation, divided by the square root of n, which is our sample size. And that's going to give us a t-distribution. It's also bell-shaped and symmetric about the mean, but again accommodates smaller sample sizes, whereas the z-score assumes a minimum of 30. And the t-distribution is actually a family of curves that are adjusted by the degrees of freedom. And the degrees of freedom are the number of free choices left after a sample statistic, like the sample mean x bar is calculated. When you use a t-distribution for a population mean, the degrees of freedom are one less than the sample size. So you can picture the sample size influencing the shape of the t-distribution curve. So like the z-curve, the total area for t is also 1, or 100%. And also the mean, median, and mode are equal, as is the case in normal distributions, such as z. Only now the degrees of freedom will increase. As they increase, the t-distribution looks more like the z-score. And after 30, it's pretty much the same thing as the z-distribution. But under 30, you can see it can flatten out and give us a different shape. And just like we can look up values on the standard normal z table, we can also look up critical values of t based on degrees of freedom, because that's going to tell us the flatness of the curve. So if we have 4 degrees of freedom and we're looking at a level of confidence of 0.95, we get 2.76. If we have 5, you can see that it goes down a little bit. So as we get more degrees of freedom, the critical value shrinks. And as we get fewer degrees of freedom, like when we only have 1, you can see how large the critical value is. It's 12.7, quite a larger number. So for instance, if we want to find the critical value t for a 95% confidence interval when the sample size is 5, we know that it's 5 minus 1, or 4 degrees of freedom. And going to our table, 4 degrees of freedom at 95, 2.776. And that's expressed graphically here, plus or minus 2.776. So these are the steps involved in constructing a confidence interval for the mean with the t-distribution. So first we identify the sample statistics, n for sample size, x bar for sample mean, and s for sample standard deviation. And that's expressed here in symbols. X bar equals the sum of x over n, and s equals the square root of the sum of squared deviations divided by n minus 1. The second step, we have identify the degrees of freedom, the level of confidence, and the critical value. Degrees of freedom is always n minus 1. So if we have 5, then the degrees of freedom would be 4. Then we find the margin of error, and that is going to be the t-value times sample standard deviation divided by the square root of sample size. Finally, based on that, we can calculate our left and right endpoints, where the left point is x bar minus e, the right is x bar plus e, and that is shown here as the interval. So here's an example where we're going to take a random sample of 20 customers from a fast food restaurant. Look at the mean wait time of 95 seconds with a standard deviation of 21. And we're going to assume that this is normally distributed and build a 90% confidence interval for the wait time of all customers. So we know n is 20. That's the number in our sample, which will give us 19 degrees of freedom. We know that the mean is 95 seconds with a standard deviation of 21. And since we're doing a 90% confidence interval, if we look at our table for 19 degrees of freedom, we come to 1.729 for our t value. So to calculate e, we use this formula where we have the t value times the sample standard deviation divided by the square root of sample size. So that's 21 over the square root of 20, which gives us 1.729 times that number is 8.1, or 8.1 seconds. So with the 95 as the mean, our interval being 8.1, we can find the left and right point by adding or subtracting 8.1. So when we set about to calculate confidence intervals, we have some decisions to make. And first, we need to ask, what is the sample size? Is it greater than or equal to 30? Yes or no? If the answer is yes to that, we use the normal distribution. If the answer is no, we need to ask, is the population normally distributed? If yes, we need to ask about the population standard deviation if that's known. If no, then we can't use the normal distribution or the t-distribution. If it is known, then we can use the normal distribution because that can be plugged right into the formula there. But if it's not known, we use the t-distribution and estimate the population standard deviation using the sample standard deviation adjusted for sample size with n-1 degrees of freedom. So here are three different conditions where we can apply that. The first is we have a sample of 50 and it's a skewed distribution with a standard deviation of 2.5. Here we can use a normal distribution because sample size is 50. It's large enough. If n is 25, now we're below 30, and if it's skewed, we have a standard deviation of 52.9. Those are not appropriate conditions to build out our confidence interval based on z or t. In the third condition, we have also a small sample of 25, but this time it's normally distributed, and we know the population standard deviation is 4.12. So in that case, the normal distribution would be used, although n is less than 30, we do know the population standard deviation.